9/17/2020. All right, so we've been talking about a difficult, challenging topic, but it is one that's important. So we left off on Tuesday talking about what we call integration by trigonometric substitution. Which is a useful, as I pointed out, technique, but it's also a challenging one. So before we begin, does anybody have a question about anything we talked about Tuesday? Does anybody have a question about, I mean, we can talk about the homework today and tomorrow. I don't even know if any of you sort of got to it yet. Hopefully you did, but I learned long ago not to assume that you guys care about calculus every day just because I do. Right? Is that a good assumption? Although you should care every day. All right, so let's talk more about this then. And when is it useful? So this technique is often useful when you see terms such as this. So you might have something like a squared minus b squared x squared. Now this looks scarier than what we talked about yesterday. And I'm going to explain this in a little more detail in a second. So bear with me. What else will this be useful for? It could also be useful for something like this. A squared plus b squared x squared. And in another common time you might want to try this sort of trick, or this, not trick, but this technique, is when you have the following. So, keep missing my pen up. So if we have something like a squared x squared, getting ahead of myself, minus b squared. So let me explain, and we tried to make a point of this sort of yesterday. Oh, hit the wrong button. Not yesterday, excuse me, Tuesday. Well, I mean, it doesn't matter what letters I use. I can use any letters, right? The point is, and we'll state this specifically. So the point being is here, A and B are numbers, while X is a variable. So I don't necessarily just have to use X. It could be any variable, but the point is to think about it that way. So why is this, you know, why is it that this trig idea that we've sort of, we called this technique, why is it useful when you see these particular things? Well, it relies on the fact that these terms, as we pointed out to on Tuesday, is they basically, these things are coming from right triangles, and I guess, and more specifically, they show their head during when we're dealing with trig identities. So if we can sort of think about why they might be useful, well, this first one, the way you might want to think about it is that you think about the first one as being something minus something x squared. Well, what we want to be thinking about when we see this particular sort of expression or terms is you want to say, okay, in my mind, I'm thinking of the Pythagorean identity. I'm thinking of 1 minus sine squared equals cosine squared. And then when I look at the second one, what I'm thinking about is I'm thinking about 1 plus tangent squared equals secant squared. And then with the third one, what I'm thinking about is I'm thinking about secant squared minus 1 is tangent squared. So let me rewrite that on the next page. So, and I don't want to go back into this in too much depth because we did it on Tuesday, but the identities, the identities, 1 minus sine squared equals cosine squared. And then the other one we would use would be 1 plus tangent squared equals secant squared. And then the other one that you would use would be, for the third thing inside the radical, secant squared minus 1 equals tangent squared. What these three things do is the identities here allow us to get rid of the radical, or eliminate, if you will. And really, or power, if it, in general. You know, we're not just saying that the only time these things can work is if you have square roots, as you'll see on the homework, is these things can be useful in other sort of particular integrals. But what I do want to point out is that these three things are sure signs to use a trig substitution. Okay, so let's see what we can get with this. And let's do one more example before we move on. So, there we go. So suppose we wanted to integrate, how about 9x squared minus 25 in the square root all over x. So here's the integral that we come across. We want to see what we can get anywhere with this. So we need to have some sort of experience to do this without guessing and checking. So what do I mean by experience without guessing and checking? If you go 3 pages back, you'll see that I have things like a squared, x squared minus b squared. So if you want to compare this to the problem we're doing, the problem we're doing has, what was it? I already forgot. Was it 4x? No, 9x minus 25. So here, this would be, in the problem we're doing, this is 9x squared minus 25. So you can think about A and B as being, A as being 3 and B as being 25, or excuse me, 5. Now, you don't necessarily have to have squares. They could be any numbers, but if we're going to give you examples, it actually works out more. It's uglier if you don't have squares. Sort of the arithmetic becomes a little less so appealing to the eye. So if we go, all right, so what is my mind thinking when I do this? What is my mind, what's on my sort of, what's going on in my mind is a better way of saying it. So in my mind, what I see is I see 9x squared minus 25. Now I have experience. So this tells me that I'm going to be using x equal to something times the secant. The question is, what times the secant? Right? So my experience tells me that this creature right here is going to get the job done, this third identity. That's what my experience says. Your experience probably doesn't say that. And so you might have to try one, or you might have to try a couple of these before you get it. It's not maybe going to be obvious to you. But my experience tells me that I want to do something times the secant. So let's sort of write that down, because it's important that you understand that I'm not just getting this. It's not obvious to me. It's experience that tells me where to start. So experience suggests x equals, and I'm going to leave it blank for a second. I'm going to say secant of theta, and I have to put something in front of it. And the question is, what am I going to put in front of it?
Need the remote.
So in order for this to work out, what's that? You say something? You have a guess? Well, you don't want to put a minus. Minus is bad. Okay, so 5/3 is Zofalger's guess, which is not a bad guess. And that's exactly going to work. So why am I going to choose 5/3? Well, because what's going to happen when I square 5, I get 25. And when I square 3, I get 9. And what's useful about that is 1/9 is going to cancel that other 9. And then I'm going to have a 25 secant squared minus 25, and then I can factor out to 25. That's one way to interpret this. So experience suggests this. And if x is equal to this, what is our dx? Well, our dx, our differential, becomes 5/3. Now, what's the derivative of secant? Many of us don't remember this one. Turns out the derivative of secant is secant times tangent. So this is one that often we have to sort of remember. So here's what we're seeing. We're seeing that what we have to do is we have to recall not just these ideas from that we've been learning recently in Calculus 2, but we also have to remember these fundamental things from Calculus 1, which we have to know derivatives. All right, so this is what experience suggests. And so if I plug these things in, what is the integral I'm left with? Well, we got to go very carefully. Upstairs, we're going to be left with 9 times 25/9 secant squared theta minus 25. Downstairs, I'm going to have a 5/3 secant theta. And then over here, I'm going to have a 5/3 secant theta tangent theta, d theta. So I forgot my d theta here, by the way. So this looks like an absolute mess. But there are some shining bright spots here. If I change color, we can help you recognize this secant and this secant go away. 5/3 go away. 9 go away. And so what remains? Well, we're going to go to the next page and write it down. But as you can see, this is not exactly a pretty looking creature, at least to most people. Most people would say this looks like a debacle, but it turns out it's not going to be that bad. So why don't we just clean it up on this page before we go forward? This is the integral. Inside the radical, you're left with 25 secant squared theta minus 25. And then there's nothing downstairs anymore, so I don't need to divide it by anything. And then the only thing that's outside now is the tangent. Now, I can, there's a couple ways to think about what happens inside the radical. You could imagine factoring out a 25, and then when you do that, you're left with 5 times the square root of the secant squared minus 1. So I don't know how you want to think about it. The way I would think about it, I'll write on the next page. The way I would think about it is, this is the integral of 5 times the secant squared theta minus 1, and then there's a tangent out here. And then the 5 can come outside, and then this becomes tangent squared d theta. So if I can sort of give you a picture of why, you might want to note that the secant squared minus 1 becomes the square root of the tangent squared, which just simplifies to tangent, provided, of course, that we're on a domain where this makes sense. So again, there are some technicalities here. You might argue, well, what if the tangent blah, blah, blah is negative or something like that? Well, we're just assuming symbolically right now. I didn't give you an interval to integrate over. So, I mean, if you want to argue technically we should be thinking about the tangent in terms of absolute values. So what I mean by that is, here's an important fact that many of us forget about absolute values. And one of the things, you should remember is that the square root of a squared, by definition, is the absolute value of a. Well, right, but we're not worried about it. That's my whole point right now. So we're ignoring the fact. We're thinking of this solely as an antiderivative. We're not interested in integrating over some particular domain right now. So another way you could really argue this too is if you think about the integral we're after. And again, most of you are probably like, what are they talking about? But it is important. This is, what is 9x squared minus 25? Well, I mean, again, you could think of this as sort of the sides of a triangle, particularly a right triangle. And so the tangent, if you want, is never going to be, we're not going to have that issue. We're going to be thinking about positive sides. Anyhow, we'll never give you a problem where that's going to matter. You can just assume that it's positive. And if you're confused by what we're saying, then I guess technically it doesn't matter anyhow. All right, so, but there are some subtleties here you have to be careful of. So the question now becomes, how do you integrate tangent squared? Now, how do you do this? Well, when we talked about trig integrals before, we talked about how to do sine squared. We talked about how to do cosine squared. And, but I never said, well, how do you do the tangent squared? So, well, easy is relative. It's not a difficult integral, but the question is, how do you do it? Do we treat this the same way as we did even powers of sines and cosines? That's the question. Yeah. Wait. Say that again. It's tangent squared, yeah. No. You're looking for an identity with tangent squared. Well, I'm not quite sure what kind of. Well, you can't bring 2 down from a tangent. No. What makes you think you can do that? That was with the natural log, but that's different. So yeah. So the natural log there. So okay. You have to be careful with how you do this. There's a few ways that you might sort of rewrite this, but there's a much easier way to do it than, don't overthink it. You can go back to the original identity that we started with. You don't even know, you see, Savalkar, you don't want to even do that here. There you go. Yeah, don't overthink this. The integral of tangent is a substitution, but this one, we just use the trig identity. So the trig identity for tangent squared, which is what we're using in the original problem. We're using this. This is 2 ways to write the same thing. And so tangent squared is secant squared minus 1. So if we write this as the tangent squared equals secant squared minus 1, oh, not an x, this is a theta. Then these are elementary because the integral of secant squared is tangent. So this is 5 times the tangent of theta minus theta plus c, and which turns into 5 tangent of theta minus 5 theta plus c. And then the only thing that we're left to do to finish this problem is we need to get back in terms of x. And so the way to do this is to draw a triangle. At least this is how I would encourage you to do it. So what is our triangle? Our triangle is, we have some right triangle here. We have some angle theta. And we are told our initial substitution is that x, if you go back, we used 5/3 the secant. So we used x equals 5/3 secant of theta. Okay, so what does that mean in terms, another way of writing that, I should say, is that the secant of theta, if we rewrite this, is 3x over 5. So that means, what is secant? Secant is 1 over cosine. So another way of writing that is, instead of doing, the cosine is adjacent over hypotenuse, which means the secant is the opposite of that, or the reverse. So this would be 3x over 5. So again, look at the triangle. If you're confused how I got this triangle and its labels, everything is coming from this. This was my substitution. And the reason it works is because this triangle tells us it works. All right, so then by the Pythagorean theorem, we know what this is. This side right here is, you know, is exactly the term that we started with. It's going to be 9x squared minus 25. Now we want the tangent of this thing, which means we need to know this creature right here. So let's call this, for the sake of space, B. What is B? B is, you know, so you know that B squared is equal to C squared minus a squared. So b is then 9x squared minus 25, just like we expected it to be. And so then that tells us the tangent of theta is 9x squared minus 25 over 5. What an ugly mess of a problem. And then how do we get done here? We write this. The 5's will cancel, so this is just 9x squared minus 25. And then minus 5 theta. What is theta? Well, theta is the inverse secant. Yikes. So this would be the inverse, the arcsecant, and you have a 5 out front of what? Well, it's going to be 3x over 5 plus c. That's a little ugly. So this is, as you can see, a very messy problem. Yikes. Yikes, yikes, yikes. Now, of course, you could write that in terms, instead of writing that secant, you could write that as cosine if you are, 1 over the cosine. You could rewrite this in multiple different ways. This is just one correct answer. There could be others. In fact, there's many equivalent ways to write this answer. Nonetheless, this is a hot mess. Does anybody have a question? I mean, this is ugly. But you do. Remember, one day from now, many years, you'll be walking down a dark alley and some criminal will approach you and say, give me all your money unless you can do trig integrals, and then you'll be saved. Should I joke about that? Probably not. This is ugly, isn't it? Does anybody have a question about this? That's correct, yeah. Although it's interesting, one of the things I learned in grad school was funny, not funny like haha, but just curiosity, is a lot of students who were educated and went to universities, particularly in like Eastern Europe and other parts of the world, they don't use secants and cosecants. They just use the trig functions, 1 over. I remember a classmate of mine, he was like, why do you do that? I'm like, I don't know. That's what they taught us to do. So everything's different. Everybody has their different way. So we'll see. There you go. You use secant. All right. Does anybody have a question about this? This brutal problem. True story. All right. Okay. So time to move on. I gave you a few of these to do and submit for homework. They, again, they're tedious. It took us about 20 minutes to do that. And that's me going somewhat slow. I mean, these problems usually take 15, 20, 30 minutes to do. I know that's not what you want to hear, but that's what they do. I think you'll survive. Of course, then you just go to Wolfram. Yeah. Hey, be nice. You're not supposed to say that. You're supposed to say awesome, O'Grady. What better way to spend your Thursday nights? That's what I say. -10 for both Emily and Eric. No negative talk about calculus. Only good stuff. There's this kid, I forget his name. He made himself rich because he just does integrals on YouTube all the time. And he does these things where like he can do like 1,000 integrals in like 3 hours and stuff. and he's made quite a YouTube fame out of it. I always say, if you get good at something, people want to pay you for it. Right? You know, I will say this: there are a lot of very successful people and intelligent people who think of, you know, doing stuff like this is just great mind exercises. You know, you might say no, but like there's these group of like finance people I follow on Twitter, and they do this every morning. They do integrals, and these are very complicated ones. Like their way to get their brain going in the morning. Actually, Volker, you might, let's pull this up. You might actually, let me see if I can get my internet here. Where's it at? I'm showing shoes now, but let's go to Twitter. This legend, I don't know if he's a legend. He might be hated by some people, but so this is one of them. This guy he's a professor / he's made himself very wealthy doing financing, stock market and stuff. But they do these things. Is that Roseanne? I don't know. So they do these crazy integral problems from these Romanian mathematical magazines. Like, look at these things. These people love it. They do it every day. They're nuts. Right? It's like their way of like getting their brain going in the morning. Mind exercise. You know, some people go to the gym and work out for your physical, but they do this kind of stuff for their mental. This guy's awesome too. I gotta get, where's he at? This dude. I want to go to this. It's just clicking on it. Let me find another one. Where is it at? He's got a lot of famous books. He's worth reading if you like reading about cool stuff like that. There's another one. Look at this. Here's some fun calculus for you. You guys would lose your mind because all it is F's. You want some real hard math problems. Here's another cool thing we can show you. So it's well documented. Well, I guess it depends on who you believe. It's the Russian math problems given to students to keep them out. Where is it at? I forget the name of it. No, the Moscow State University. Yeah, they're usually called the Jewish problems. That's right. Because apparently, and who knows, I don't know the politics of what happens in Russia, but the story goes that you can read all about this, that in Russia, Moscow State, they wanted to keep Jewish people from going to universities for whatever reasons they might have. But anyhow, they would give these, if a Jewish student would do well on these entrance exams, they would make them take these other tests. And they would give them these insanely hard math problems. You guys should check them out for fun. And there's been a lot written about them. Oh yeah, so you want to blow your mind too. The Math Olympiad problems are awesome. Cool problems. And so there's this dude. Yeah. So it's wild, and this wasn't even that long ago. This kind of stuff was still being done in the 80s. And there's a lot of documented evidence this kind of stuff happens in lots of places, not just in Russia, but read about the history of like standardized tests in the United States, like the SATs and stuff, why they started, what the goal of them was to do. I call them wealth tests because you ain't got to be smart. The more money you can pay tutors to teach you how to take them, the higher scores you get. But this famous mathematician who escaped from Russia in the 80s when it was the USSR. This guy is, he tells the story of how, so I guess he has Jewish blood in him, and that was, so he escaped. They wouldn't let him get a PhD in Russia because he was at Moscow State, so he left, and guess where he went? Harvard. That's the one thing, I shouldn't say this out loud, so I won't say it. You guys might get in trouble, or I'd get in trouble for saying it. but you know, we're good at importing smart people from other places. That's one of our skills here at the good old US of A. But anyhow, he came to Harvard to work. He was a professor at Harvard, and then they gave him a PhD. So he's written a few books. This guy is pretty cool. He's an interesting mathematician. That's what we can do. Famous Math Olympiad promise. Want to do this stuff. And by the way, you guys, it's worth pointing out too. Here's what's worth pointing out is that there are some people who do take, like, it's interesting. So many of us now say, why do we learn integrals if a computer does them for us, right? Well, it's still, there's something to be said about, you know, human endeavor and perseverance. And if you go to a lot of universities, they have, does everybody here know what a spelling bee is? Right? You know, spelling bees, they have integration bees. Like if Pitt has one every year, and they have monetary prize. It's like a big deal. All the nerds get together in an auditorium, they integrate all these crazy things. MIT does it. You should watch these videos anytime you want, anytime you're bored. Well, let's see what the MIT, the integration problems are. So in order to qualify, you have to do a written test. Yeah, and MIT is a bunch of smart people. I shouldn't say that. That's that broad brush if there ever was. Yeah, this is what I always say, the nerds. I wish they invited me. Can you see me in an integration bee? But there are a lot of people that this is interesting to them. So here's a good integral. Cosine, can you imagine this beast? Cosine to the 2020. That's an even power. You'd have to apply that strategy we did. That would be something fierce. That would be some algebra. There's got to be a trick to that, right? Okay, anyhow. Anything. Yeah, that's right. Minus 20 for everyone. We could ban everybody. Can you imagine? Wonder like, what do they do in like elementary schools? And if people like, do they ban you from Zoom? Like, what if someone like snuck into our class? We'd have to like make it password protected. How about that? I was talking to you guys about this. This was interesting to me. I was watching the news and they were complaining. They were complaining that some teachers were like requiring students to like show their faces, which I think is kind of rude because I don't know where they're at, right? You know what I'm saying? And then they wanted them to be dressed a certain way. Yeah. Who doesn't take Calc 2 for fun? You guys can have your 10 points back if you enter the MIT integration bee. There's videos of it on YouTube if you want to talk about hystericalness. There you go. All right, anyhow, let's get back to math because you guys know me. I'll end up doing this stuff for 3 hours. We won't learn anything new. Just random O'Grady thoughts. Okay, so what we're going to do now is we're going to talk about, yeah, I can imagine that. I don't know why they do. Like, here's the thing I say, Eric. Here's the thing. Why? I don't know any of your situations right now. Maybe you are in a dorm. Or maybe you're in an apartment with other knuckleheads. Or maybe you're at home and you have babies and pets running around. Maybe you don't feel comfortable showing your face. I ain't mad at you for it. And I sure as hell ain't going to stand there and watch you take a test and look at you like this through Zoom. I heard people want you to do that too. I'd probably be doing push-ups the whole time if I was a student. I'd be listening and mentally doing these integrals in my head because that's what us geniuses do. We don't ever write anything down. We just do it mentally. All right. Okay, all kidding aside, we got to talk about, again, there's homework problems on those things, and we still haven't done the famous arc length of the, we still haven't done that yet. We asked you to do that for homework, so hopefully you'll keep trying that before we give you the answer. Or you'll look it up, which steals the fun. Now we want to do another technique of integration. So let's move on. And this one is more sort of based on algebra in techniques from algebra, and it's called partial fractions. So partial fractions is useful for rational expressions. So if you don't remember what a rational expression is, it is the ratio of two polynomials. So, did someone say something? I thought I saw the flash. So I don't know if you're alluding to these ones, the Fogger, but yes, these integrals are tedious too because there's a lot of sort of prep work to do them. Now, that being said, they also turn up in many important applications, so you don't want to just ignore them because they're tedious, or once again, because you ignore them because you figure, well, software can do them. Because there is, again, there's a deeper idea here, and I like to think of this in a fancy way, but it's, you know, I'm kind of just doing it, saying it, but I like to think of problems like this as great examples of a bigger theme called reverse engineering, where we know how to do something one way, but we're being asked, and we don't realize it yet, to do something in sort of the reverse direction. And sort of what we have to do is figure out how to reverse our process to make something work. Now, we've seen this a bunch in different areas. I mean, you see it with arithmetic. You have squares and square roots. Right? You have numbers and inverses. We've seen it in algebra before where you do certain things. And even in calculus, you can think of integration and differentiation as sort of reverse processes. And here, that's a theme in and of a theme, I guess is a way of saying it, because what we're going to have is we're going to have a fraction, and we want to integrate it, and it turns out that the way to do it is to take this fraction and write it as quote unquote simpler fractions. And that's interesting because most of what you guys did in algebra, things you would have learned in your many courses in algebra all through secondary school and stuff, was the opposite. It was take multiple fractions and add them together, right? Or take these fractions and multiply them. Very rarely did they ever ask you to say, here's this big ugly fraction, write it as 3 fractions. But it turns out that doing that is going to make things useful for us. So let's look at an example right away to sort of see how this might go. And so let's look at this. So let's motivate. So let's just consider this. We want to integrate 1 over x squared minus x. Now, a very common sort of jump at how to handle this, what we often do as amateurs by mistake is we say, okay, if you've practiced a lot, you might think right away to let u be the denominator. And it's possible that if you set u to be the denominator, that could work. So let's think of it that way. So a common first attempt might be, say, y equals x squared minus x. dy equals 2x minus 1. So let's say we try this. So if we try this, then your integral, oh, I forgot my dx here. So if I try doing this, then this integral becomes 1 over u, or excuse me, 1 over y. Now, what is dx? Dx is, if I substitute that in, this is 1 over 2x minus 1 dy. So here we have two variables, and more importantly, it is not at all obvious how to quote unquote remove one. And let me emphasize, legally. Of course, you might just say, I'll just get rid of the x and then it's fine. It's not legal. And then you might say, well, what, oh, that x squared minus x, maybe I can do some trig stuff. And it turns out that's not going to be very useful either. And once we try a bunch of stuff, we might feel like there's no hope. And it turns out there is hope. We just have to figure out how to get that hope. So instead, note that the guy we started with can be written as this. And I know it's not going to be something that you think about, but to someone who has some algebra, sort of a solid understanding of algebra, what they might notice is that this suggests that 1 over x squared minus x is the sum of two rational expressions. Now, why do I say that? Well, let me emphasize why I say that. If I write 1 over x times x minus 1, suppose you're back in algebra class and they say, okay, here I have one fraction. I have something divided by x, and then I'm adding something divided by x minus 1. If you added them together, the common denominator would be x times x minus 1. So this suggests that somehow, some way, you have some number a over x plus some number b over x minus 1. Again, I'm using what I called earlier this reverse engineering. Like, I'm thinking, and this doesn't even have to come from algebraic expressions. You might imagine that, take a number, take something like 1 over 12. Well, 1 over 12 can be written as the sum or difference of two fractions. Notably, how can I write 12? Well, think about 1/12. If I switch, let me just change colors for a second. If I take the number 1/12, I can write this as something. Particularly, I can write it as something over 3 and then plus something over 4. Well, what would it be? Well, if I wanted to multiply these together, this would be 4. And this would be, okay, so maybe let me be a little more clear. So what if I put an A here and a B here? So then what's the right-hand side? The right-hand side would be 4A plus 3B over 12. So can you think of two numbers, A and B, that would make this work? And the answer would be set A equal to 1 and B equal to -1. And then you would get 1/12 is 1/3 minus 1/4. Check it for yourself, right? So you guys spent a lot of time, just like I did in classes many years ago, moving right to left, taking 2 and turning it into 1. But now we're saying that it might be useful to start with 1 and move it the opposite way into 2. Does anybody have a question about this? Now, the question is there a systematic way of doing it? And it turns out there is, because it turns out that not only does this suggest it, but it is always true. So it's worth writing that down, and we're not going to go deep into it, but it is a fact. So first and foremost, how do we sort of so fact, if the degree of the numerator is smaller than the denominator, and the denominator factors, so don't forget, what's the degree? The degree is the largest power. And remember, we're talking about rational expressions. So these are polynomial divided by polynomial. So in the denominator factors, we can always decompose a rational expression into the sum of other rational expressions. So instead of going through the scary algebra, it's better just to do an example. Now, when I use the word sum here, by the way, it's important to note that it could also be a difference. So I say sum, but as we saw with that numeric example, it could be a difference. So the question then becomes, how do we do it? So there's a few ways you can think about this, and some of you may have seen this. Some algebra instructors actually do this, others don't. The first way is, if it's simple, you could guess and check. You could reason it pretty quickly. So that actually works with the one we're dealing with. Let me go back for a second in case anybody has a question. So if I go back to this creature right here, it might not take much work for you to to think about what should you choose A and B to be. So, for example, if I choose A to be -1 and B +1, it'll work. You could verify that for yourself. So one method is to, what I say, guess and check. And that is 1 over x times x minus 1 is equal to -1 over x plus 1 over x minus 1. So you could check that this works. So what I'm saying here is, since the denominators were simple, the factors were simple. And I mean, when I say simple, I mean relatively speaking. One is x, the other is x minus 1. There's no constants floating around. There's no constant in the numerator. So since it is relatively simple, in my head, I say, okay, if I multiply and if I do this and if I do the, you could check. So just for fun, let's check the right-hand side. So -1 over x plus 1 over x minus 1 is the same as -x minus 1 over x times x minus 1 plus x divided by x times x minus 1, which is -x plus 1 plus x all over x quantity x minus 1, which checks. It does, in fact, work. Now, is guessing and checking efficient? No. It's only efficient if you're very well versed. And even if you are very well versed and have a good, solid understanding, this is not the best way. But before we show you another way, we might as well finish this integral. Does anybody have any question? And by the way, we'll show you, actually, let's just show you a more sort of algorithmic way. So here's the other way I would, and this is probably the way you should go, 99 out of 100 times. So in general, it's probably best to logically deduce the decomposition. So here's one way you can do it. So I'm going to start with 1 over x times x minus 1. And I want to determine the number a and the number b that make this true. So this statement is equivalent to the statement here. So I'm taking some liberties with hoping that you guys are feeling okay with some algebra. So all I'm doing is I'm saying there has to be a number A, there has to be a number B where this is true. How do I deduce it? So I'm going to set the left and right-hand side equal. Now I'm going to perform the addition on the right-hand side. How did I do that? I got a common denominator, which is x times the quantity x minus 1. And then upstairs I have this sum in my numerator. And one of the things that's nice to know now is we can ignore the denominators, because the only way these two fractions are the same is if their numerators are the same. Because their denominators are already there. We can multiply them out or get rid of them, if you will. So really the only equation we need to satisfy is this. Which I am going to rewrite as 1 equals negative a plus the quantity a plus b times x. So this is the equation I want everybody to ponder. So you can reason either up from the bottom to the top or from the top to the bottom. These two expressions are the same, provided what's in the red sort of cloud is true. Now, there are only going to be one number A and one number B that make it true. So let's look at this equation. How many x's do we see? I see one x. Do I see an x on the right-hand side or the left-hand side? The right-hand side. So if this thing in the cloud is going to be true for all x, what must a plus b equal? It has to equal 0. Because the only way for this thing in the red cloud to be true is if that x is gone. So that x being gone, the only way that happens is if when we add a and b, we get 0. So what I'd like to do is I'd like to draw some sort of line to make sure we understand that my reasoning is happening here. What do I mean to logically deduce? Well, what I've just logically deduced is the following. The red cloud forces a plus b to be 0. And it also forces a times negative 1 to be equal to 1. Because if a plus b is 0, that term goes away. This term is not there. So then that means negative a equals 1. So the only conclusion then is we conclude, as we already guessed before, we conclude that a equals negative 1. And if a equals negative 1, b has to equal 1. So this is called matching coefficients, this method. We having fun yet? I feel bad. I hate this hybrid stuff. It's no fun. I want people in here. I want to talk about life and laugh and ask questions. Say ridiculous things that I shouldn't say when we're recording in case the authorities hear me say something. Then I get fired. Then they have to bring in some other numbskull to teach you guys calculus. And then I'm sad because I like getting paid. So no matter if you guess and check or we logically deduce it, there's no other options here. Now, I know that this type of reasoning you're not very much used to, but I encourage you to really think about this. Some of you will have to use this method in other courses as well, depending on what your major is. And so it's worth trying to understand now. Any comments of this question? Okay, so we can finally integrate then. We finally can integrate. So what's the moral? The moral is the integral that we started with, which is x squared minus x downstairs, is the same thing as this integral. But this integral we just found is negative 1 over x plus 1 over x minus 1. And these are not difficult integrals. I'm going to rewrite this just because I hate that minus sign out front. It makes me nervous I'll mess up. And so this just becomes the natural log of x minus 1 minus the natural log of the absolute value of x. Isn't this fun? What a beautiful integral. Does anybody have a comment? You have a question? So how do you get good at these? You practice. You don't watch me, you practice. Now, of course, you're going to say, well, I'll just go to Wolfram and it'll tell me the answer. And again, I can't stop you from doing that. I can only encourage you to use Wolfram as a resource, not a way to get 5 points on your homework. Because I'll tell you what, the exams that you're going to take, especially with me, computing the integral is only part of it. There's going to be it's going to be more about how do you understand and write things than it is that you get the right answer. And you'll see what that means when we take tests. And it is Calc 2, which means most of you will flunk it anyhow. And then we'll curve. I'm just kidding. Well, maybe not. I always say this is like one of the hardest classes. Calculus 2. Let's Google that. That's always fun to do. Let's see what the Google machine asks us to do. What's the most difficult course at university? Let's see. Hardest, biology, computer science, civil engineering. There you go. Let's ask what these people say. And Cura. Nursing. Well, there you go. Music. There you go. No Calc 2. Well, then maybe we'll all get A's. Ooh, physical chemistry. Everybody flunks that, though, because it's all math. Interesting. Architecture. I love opinions. This is good. We get to learn these things. Isn't this fun? $13 most difficult. This is good. Oh, this is going to be easy. You didn't even get, no, these are majors. Physics. How was physics number 1 or 6? Physics is easy. Let's see. Let's see the rankings here. I love these polls. Chemistry, neuroscience, mechanical, engineering, petroleum engineering, bioengineering, physics, astronomy. This is so good. I love when they say these things. This is when your minds start to explode. Hours spent each class a week, 20 hours. Ha! Some of you won't even spend 20 hours all semester on calculus. And you're like, I want to be an engineer. The world we live in. Very good. Architecture is pretty cool. I once thought about doing that. All right. It is time to go. That was a fun class. Well, let's see. That's one more question. This is always fun to ask too. Most lucrative and happy major. Let's see. These are the college majors that'll make you the happiest. This is, let's see. Computer science, electrical engineering. Look at this. I guess there's one very nice theme in all of these. Salary. That's right. What a time to be alive for show. All right. I love these things. They make you so happy. Let's see what else. Most lucrative major for pay and let's do this. Best major. I like, this is what we discover. We encourage you to do stuff for pay and happiness. You already read that one. I like this. Does a college degree make you happier? Probably not. That is so cute. Here we go. 11 highest paying jobs with job satisfaction. This is always useful. Let's see what Kate has to say about this. Radiation therapist. That sounds good. Median salary. Very good. See, I would think an elementary administrator would not be. Well, I guess they get paid well. Physical therapist. Good. Pediatrician. Audiologist. Optometrist. Dental. I think they're fake. Public relations manager. Very good. There you go. Now you could be happy. All right. Anyhow, this is fun. Nothing like putting pressure on 18, 19, and 20-year-olds to think about what they're going to do 10 years from now, all right? The stress is already bad enough. You have a question? No? All right. I'm just kidding. Anyhow, guys, seriously, I know the end-all be-all isn't calculus, but I do encourage you to try to learn this. There's a sense of if you figure this stuff out, because it's difficult and challenging, there's a sense of like personal satisfaction. Not that you might not care, but you know, check it out. Anyhow, thank you guys. I will see you tomorrow. What group is it tomorrow? I mean, I think tomorrow's technically A, but there's enough room in here if you all want to show up. So if you want to show up, I'll be here. Well, I'm going to be here no matter what. So take care, guys. Thank you very much. And have yourselves a good Thursday night. All right. Thank you all.